Welcome everyone to my presentation on proving why it's a true statement that an inner product on a real vector space is a symmetric bilinear form. Now, to prove my point, I'm going to use this theorem here, theorem 6.1, which is found in Linear Algebra 4th edition by Fredberg and others, right? And of prime importance is part A of this theorem here. Now, I'm going to read the theorem from the top. Let V be an inner product space. Then for X, Y, and Z in that inner product space, and for C in the field here, we have the following statements. These statements are true, and as I said, I want to focus on part B, which states that the inner product of X and Y plus Z is equal to the sum of these two inner products here. That we have X, Y, and XC. So, when you were dealing with inner products, right? What happened is that you have the components of vectors to deal with, right? Take, for example, in dot product, you just multiply the X and Y component if you have vector X and vector Y, and you keep adding them. So X1, Y1 plus X2, Y2 plus X3, Y3, and so on till you're finished, right? Now, when you're dealing with inner product spaces now, the components that you will be dealing with are the vectors themselves. As you can see here, we have the inner product of X and Y plus Z, that is an A, is equal to the inner product of X and Y plus the inner product of X and Z. These components in here are vectors themselves. Now, what I did, right, I defined vectors X, Y, and Z, and I list the components of these vectors, X1, X sub 1, X sub 2, and so on. Look at the vector Y, Y sub 1, Y sub 2, and so on. The vector Z, Z sub 1, Z sub 2, and so on. By the theorem here in A, in part A, I'm going to do some expansion, right? So I have the inner product of X and Y plus Z is equal to the sum of these two inner products, XY and X. Now, XY, we can see that here, we can think about an inner product, a dot product, right? And the X and Y components, we just multiply them and keep adding up the results, right? So for the X and Y, the inner product of X and Y, we have X sub 1, Y sub 1, plus X sub 2, Y sub 2, and so on. And then we still have to add at the back here the other inner product of X and Z. Now, the inner product there will result in X sub 1, Z sub 1, plus X sub 2, Z sub 2, and so on, till you reach the final component in both vectors, right? Now, I like to do some rearranging where I put these components with a common I, J components together. Like take, for example, I have X sub 1, Y sub 1. I'm going to group that with X sub 1, Z sub 1. Then I move on to X sub 2, Y sub 2. I'm going to group it to X sub 2, Z sub 2. So I'm putting these components, grouping them together according to the sub ij components, the common sub ij components, until I finish with all of them here at the back. Now, that will lead me to some factorization. As I scroll down here, you'll see I did some factorization at this point here. Good. So we have some factorization here. So I have X sub 1 times Y into Y sub 1 plus Z sub 1 as a factorization of what we have at the top here. And this one here, X sub 2 into Y sub 2 plus Z sub 2 is a factorization of what we have at the top here, and so on. So this will factor out until we reach the final components. Now, what I did next, I take the X sub 1 and I place it at the back of the bracket here, right? Because we know if we deal with that product, it commutes, right? X sub 1 times this C is the same thing as y sub 1 plus z sub 1 times the x sub 1. Just change the order here. It doesn't really matter, right? So I did that. Now, what that means, right? If we are to transform this into a vector component form, right? Generally, we notice that we're dealing with x adding to z, y adding to z components, as seen in the first part here. And then I'm multiplying that by the second component from this with a component from the second vector, which is x sub 1. You can see that at the bottom. So I'm taking all the y sub 1 plus z sub 1 components and I'm multiplying it by the x sub 1 components. And I'm doing that throughout. And you can see that generally boils down to y plus c, the inner product of y plus c. So by definition of here that we have taken from the same textbook, we can see that a bilinear form H and a vector space V is symmetric if we have here a function which takes these two vectors x and y, and that is equal to, if we take the same function again and apply it to the same two vectors, but this time we change the order, and we'll have the same results. The left-hand side will be equal to the right-hand side. The only thing we change the order which the vectors appear. Now, if you notice at the top here, I have here x appearing first and the y plus z at the back, right? Now I have here the y plus z appearing first and the x appearing at the back here. Sorry, just change that. Yes. So you see, definitely we have something here similar to what is stated in the definition. Hence, I conclude that indeed an inner product on a real vector space is a symmetric bilinear form. Thank you for listening.